Powered Parachute Handbook 2-2 Aerodynamics of Flight. Pitch motion, controlled by thrust, determines the climb or nose up and descent or nose down of the powered parachute. The lateral axis governs this movement. Turning, associated with the longitudinal axis, is initiated by manipulating the wing trailing edge, akin to an airplane's aileron and rudder controls. The powered parachute, designed to fly directly into the relative wind, avoids significant turning about the vertical axis, automatically correcting any yaw. Ground effect, affecting airflow and turbulence patterns close to the ground, is minimal for powered parachutes due to their typical altitudes above half the wingspan. The center of gravity, a crucial point for rotational movement, remains generally in the vertical center of the fuselage. In two-seat powered parachutes, it is usually positioned above the rear passenger seat, offering stability. Ground effect manifests as additional lift during takeoffs and landings. Moments, pivotal in rotation, depend on the force and distance from the center of gravity, cg. Powered parachutes lack a horizontal tail due to their airfoil's fixed position relative to the cart. The pendulum effect, generated by the weight of the cart beneath the center of lift, stabilizes the aircraft. Thrust line moments, influenced by the propeller's thrust above or through the center of gravity, can affect pitch. A high attachment point enhances stability, minimizing pitch during thrust application, and reduces swinging in turbulence. However, it creates a negative P factor and demands more thrust for the same climb rate due to increased wing load. Understanding these factors provides insight into the complex dynamics of powered parachute flight, from pitch control to the impact of moments on stability and performance. When cruising over a smooth runway with the rear wheels just an inch above the ground, the nose wheel sweet spot should be between 7 and 11 inches above the pavement. This delicate balance ensures the wing is correctly attached to the cart. Too far forward, and you've got a high-flying nose wheel. Too far back, and your nose wheel is practically touching the ground. Follow the manufacturer's manual. It dictates where the wing should hitch a ride on the cart. You wouldn't want the nose wheel playing limbo during landings or pointing in odd directions, messing with thrust and causing a headache for everyone involved. Align it just right, and you're cruising smoothly. Tilt it too high or low, and you're in for a bumpy ride with less thrust and an unwanted side of P factor. A stable aircraft is like a well-behaved pet. It goes back to its comfy spot after a little disturbance. The pendulum design in powered parachutes is like a built-in stabilizer. It's always trying to bring the cart back under the wing, giving you that positive dynamic stability. So, no matter what chaos you throw at it, be it turbulence or some fancy maneuvers, once the turbulence stops, your powered parachute is back to its happy, stable self. And guess what? That stability also ties into the angle of attack or AOA. In normal flying conditions, that angle of attack stays pretty consistent, like your go-to order at a favorite restaurant. The powered parachute is designed to avoid stalls, too high angle of attack and wing collapses, too low angle of attack. Stick to the limitations in the manual, and you'll keep that angle of attack just right, cruising through the skies like a pro. Imagine you're coming in for a landing in your powered parachute. You gently pull down on the trailing edges of the wing, and voila, you're flaring. It's like applying the brakes in the sky. But here's the catch. When you flare, you're also cranking up the angle of attack. It's like giving your wing a little extra lift, a bit more drag, and a temporary boost in angle of attack. Picture it as if you're lowering the flaps on an airplane. More lift, more drag, and more angle of attack. Now, this flare-induced angle of attack increase is a quick fix. Your wing might slow down a bit as the pendulum effect swings the total weight forward of the wing. It's like a pendulum. The cart swings forward, angle of attack goes up, and voila, more lift and drag. Once the pendulum swings back, your wing is back to its usual stable flight configuration. So, enjoy that little angle of attack boost, but know it won't last forever. Ever seen a powered parachute do the porpoise during takeoff? It's a dynamic pendulum effect at play. When you hit the throttle hard, the extra thrust swings the cart back and forth until it finds its groove. It's like a brief waltz before stability kicks in. Gradual throttle increases can tone down this routine during takeoff. Every aircraft has a critical angle of attack, that point where things get wobbly and the wing stalls. In your powered parachute, the manufacturers have got your back. They've designed the wing to stick to a specific angle of attack and airspeed range. As long as you stick to the operating limits in the manual, stalls are like distant nightmares, far, far away. But hey, we're all human, and sometimes we unintentionally push the limits. Things that could nudge you towards a stall? A sudden full flare that's pulling the wing back hard, a quick full throttle in a climb, a sudden throttle reduction during a steep climb. These are the culprits. So, be mindful and stay within the PO limits to keep the wing happily lifting. And talking about turns, torque is the name of the game. The turning propeller wants to pull your cart in the opposite direction. Manufacturers get creative to counteract this. Dual propellers, different riser lengths, tilting the wing attachment, or adjusting the powered parachute frame. It's all about keeping your powered parachute on a straight and narrow path. Embark on a journey through the intricate dynamics of powered parachutes, where weight, load, and speed harmonize in a captivating aerial ballet. Envision yourself gracefully gliding through the sky in an 800-pound powered parachute during a serene gliding flight. Here, lift and drag collaborate seamlessly. Lift at 759 pounds, drag at 252 pounds, resulting in a gentle 800 pounds of vertical force. As the transition to level flight unfolds, complexities arise. The absence of the vertical component of total drag demands additional lift. This can be achieved by tweaking the speed or adjusting the angle of attack. Despite the seeming subtlety in these numerical values, a rule of thumb prevails. Assume a constant speed and angle of attack with changes in throttle. Now, let's delve into load factor, the force influencing speed changes. In straight and level flight, lift and weight engage in a balanced duel. Yet, when executing a banked turn, lift loses some of its vertical component, necessitating an increase in lift to maintain equilibrium. Under regular flying conditions, maintain a constant speed and angle of attack. Weight dictates steady-state airspeed, with more weight resulting in increased speed and/or angle of attack. Lighter weights translate to slower speeds, lighter wing control, and gentler descents. Heavier carts lead to higher speeds, increased maneuvering effort, and faster descents. The wing's design and cart weight collaborate to shape your powered parachute's performance.